So, good afternoon. I hope that the screen and the video are both working fine. If not, please just shortly type in the chat. I think we could start. Sticking to give it a few more seconds. The video is good, perfect. Thank you for confirming that. So again, good afternoon. My name is Daniel Butnaru. I'm a principal architect in Roche Pharma Research and Early Development. And I have been working together with my colleagues for over the last 2 years to help our organization to bring more machine learning models into production. So we have a kind of a central function where we are helping various data scientists to bring their models into production, so bring them into places where they provide value. And we have the particular challenge that we are faced with a lot of diversity on many levels. On one side, diversity in terms of the models that we want to help with. So they're very diverse from different categories, different business cases, different frameworks. And that's in itself is a challenge to kind of come up with an MLOPS approach which helps all of these models. And on the other side, we have a lot of diversity in the targets where the models are supposed to deliver the value. So there are many places where the inference results have to go to, and due to the size of our organization, that is not by any way standardized. So given this diversity that we have, we still had the chance and the task to come up with something which works for many of our models, also the ones which are coming on our roadmap, to help them to bring them into production more consistently and more faster. Now, I would like to start with just highlighting a bit of the diversity that we are dealing with. We had initially a long backlog of models, of which we selected 5, these 5 on the slide right now. And we did the selection so in a way that they have sufficient diversity in there for us to kind of stretch our limits and not to kind of come up with a solution for machine learning operationalization, which does not cover all the use cases that we have. So just a few of them. So from a business case, they're quite diverse. They come from different parts of our research business. So one of them is a monoclonality assessment. It's an image classifier that looks into images to see if there's a single cell or several cells. The next one, as the name says, predicts toxicity. The following one is looking at protein folding and tries to come up to figure out any post-translational modifications that can come up. The next one is very interesting, and we'll get back to that one in a second, is a molecular property predictor. So it takes in a small molecule and outputs around 100 plus properties of that molecule. And the next one, again, or the last one on this list here, is trying to predict regions where an antibody would best bind. So they come from very different parts of the drug discovery pipeline. They have different modalities. So the first one is image-based, while the other ones are relying on feature tables. In terms of languages and frameworks, we are a very research organization, so it's very hard to standardize. There are very different people coming from different locations, and we take for granted that anything goes in terms of where the language will be used or the framework. And the next diversity factor is also that if you look at the business cases, they're not just one model. Some are, but some are many more models packaged into a single business case. And that raises significantly the complexity into handling that one. For example, the molecular property predictor has hundreds of models, different models with different frameworks and different languages trained, but they all do the same. They predict properties for chemical compounds. In terms of the inference deployment, you would have batch and online deployment of the models. And the last column here, which is also very important, is where do you deliver this inference, right? Where do you deliver the results? And here you have a broad scope of possibilities, from some custom dashboards for quality assessment, as the first model is the case, to directly into a relational database where you have to write the results there, to various operational systems where the scientists use on the day-by-day basis to make decisions based on the model outcome, or the model itself makes a decision. And another one for the molecular property predictor is a chemical design tool where a user designs molecules in there. And to give you kind of a feeling of how far we looked into this, or what was our approach to all of these models, we can look at this molecular property predictor first to go a bit through it and understand what it does. Yeah? So what we have here at the top, we have the models themselves. So here, this MLPP models. Yeah, this is the part where the models are being already trained and they're running somewhere, right? They're available. The flow around this particular models involves a scientist analyzing some data and coming up with some design ideas. Design ideas are a few molecules, a few small molecules, which are interesting from a particular point of view. And then they're being thrown into these models to extract or to collect various properties, these 100 plus properties. Based on these properties, not all of these design ideas are good, only some of them are being prioritized, are tweaked one way or the other. And again, we go back to the same step of creating or generating new properties and going back to see if the new properties for the new designs are better or worse. When this loop exits or is finished, we actually go into the physical world where the small molecules are actually synthesized and tested. And what's great about the physical world is that you can test or you can measure the actual properties, which then again are data for our training for future models. So what's important in this flow, it's not so much the flow itself or the details, it's the fact that one lesson that we have applied is that we looked at the model from the beginning, its entirety. How is it actually being used? So just deploying the model and having API somewhere, it's very valuable, but actually the entire usage of that model dictates a lot, also the implementation and everything, the scaffolding needed around the model to make it work. And getting it in our organization, getting it in the right place, in the right quality, and making it really available is very critical and goes way beyond just making the model run somewhere. And that was a lesson that we learned from all these activities. Now, how do we go overall for all models? So we have a particular approach where we thought, okay, a very simple technique we all use all the time, dividing and conquering. So what are the three blocks or the three things that we would like to, that we think that the MLOPS process is about for us? And we identify three different chunks. So we have, first of all, the training data, so getting the trained data. And this involves capturing and collecting the raw trained data from the various operational systems where this data might be available. Now, that data collected from operational systems usually is not ready, so we transform it usually in something we call oven ready, in the sense that it's ready to be used, thrown at the model for training, and setting up any automation around this data collection for the training. So this is also a very important step. The next block here is the model itself. Yeah? So these are all activities around the model. So here's about training and retraining models, about having scoring and quality of the models, and very important, having a release process for that model and the corresponding environments where the models are released to. And that's also itself quite a fun task to do. The last block is the usage of the model. And this is also a very important one, because here we have to deal with delivering of the online or batch inference, so making it available somewhere. Then anything that goes around custom model APIs, adaptations to make it more tractable for external consumers to be used. We're going to get back to that in a second. And considerations around quality of service and scaling of that particular model. So these are our building blocks that we kind of split it, we wrapped our minds around them like that. And given these building blocks, we started by applying also now our first principle, let's call our first pattern that we applied in our setup. And it has to do with separating the ops related code from the model related code. Yeah. And what does this mean? It means that in each of these phases, we try to see it as having two parts. One is the model-specific part, yeah. So parts about which come from the data scientist or data engineer, and they're referring to specifics of that model, like a particular way of training, a particular data transformation that is necessary on the data to make it trainable, to make it ready for training. And on the other side, we have the ops-related part. These are the pipelines, the scaffolding, the infrastructure, and other activities which are not necessarily specific to the model, and they are more common, or they're more using the same tooling. And this distinction, we kind of follow it through in all parts. So on the data part, on the model part, but also on the usage part of the model. So we separate in between these two different activities. Concretely, this means that there are at least two repositories. So one, the model owner repository, which contains all the model specifics in there. And another repository, at least another repository called the ops repo, which contains all the specifics to put this model in a production state. And this can contain, depending on where we are in this block, can contain various different things. It can contain configurations for a GitOps approach. It can contain a custom, it can contain deployment scripts for microservices on Kubernetes. It can deploy various ops-related activities. So on one side, so we have the users or the data scientist, which gets the chance now to work in his own space, in his own repository. However, he does provide an interface to all the ML and data operations. Now, that's very important. Yeah, this is the first interface, and there's our pattern that we applied separating these two things. On the other side, the MLOps engineer, he maintains the ops pipelines in dedicated repos and relies heavily on the interfaces provided by the data scientist. And even though we do make this distinction on this slide between these two different persons, in reality, it can just be roles that the same person has. So we do have also data scientists which go through to do both things. However, the separation also helps them to have a very good understanding of what is actual model-related code and what is ops part, infrastructure activities that are somewhere else. Now, this was our first interface that was first pattern that we applied, is to separate things. And this allows us, and the separation is very important, as it allows us to deal with the diversity. So we do not, we assume that the specifics are separated from the ops part, from the infrastructure. So we can help many data scientists with infrastructure, with tooling, with pipelines, but we just require them to package their data science related activities and model code separately. And how is that done? So it's in a way we rely on a command line interface plus a container. And so the idea is that the model owner, so the data scientist, is packaging inside a container an interface which exposes the majority or the most important operations specific to that particular model. That can differ a bit depending on the model, but the classical ones, I mean, the possibility to train the model, to score it, or to do any pre-processing on the data. So these commands are available inside the container, and they're packaged, and that is really the currency or the exchange between the data scientist and ML engineer is this particular container, which then is being leveraged by the operationalization pipelines in a way that it's very transparent. So you leverage just the commands in there. So you build the pipelines. We are using Kubeflow in this particular case, and basically in all the steps we're leveraging this container and using the operations inside there to orchestrate different things, be that data pre-processing, be that model training, or even model deployment. And all these operations, they leverage the container built by the data scientist. And this works very well for many models because you abstract all the dependencies, you have a clear interface, and in case something goes wrong during either pipeline execution or other things, you have a much easier way of finding out where did something go wrong. Is it on the container side, building the container? Is it in the pipelines? So it's much more easy to kind of figure things out, and also has a bit more clear responsibilities in the whole process. Now, this was the first pattern, so this separation between ops-related and model-related code. The second pattern that we focused on is about the consumption part, right? So we did mention on the first slide that the inference delivery happens in various locations: custom dashboards, databases, operational systems. And on the other side, when we build the models, we usually either build pipelines for the batch part of the execution, yeah, and we use heavily Kubeflow for that, or we deploy the models individually as online models, right, as microservices with APIs. And in the case of, for example, of the molecular property predictor, you have hundreds of these endpoints being deployed and versioned and managed individually, so separate from each other. And now the question is, of course, is how do you offer them to the outside, right? And we have this diversity on the consumption part, and that we have to cater to. And our approach to that is twofold. So for the batch path, we are leveraging heavily message queues. So we decided to kind of put this intermediary layer between all the consumers of the batch inference and the actual pipelines that actually do the inference, and leverage. We had Confluent Kafka mostly in use here. Leverage it as a buffer, but also as a way of scheduling all these activities around the inference. And that has many advantages, from better scaling to resilience to retry mechanisms and so on and so forth. And it also hides away the producers from the consumers, and it allows us to change on both sides quite flexibly without actually having to deal with advertising the changes that have been done on one or the other side. Now, since I have missed two questions in the chat here, so maybe I can go back to them. So to your question, Benjamin, yes. So for each project, we have at least two repositories: one for the ops repo and one for or is it shared between use case? No. So the ops repo is specific to a particular model. Yeah. So we separate for each model. We have at least two repositories: one for all the model-related code and one for the operationalization part, because that can also be very different from different models. If it's a batch one, an online one, there will be different operationalization activities going on in there. To both create. Now, the second question here, if both ML scientists and MLOps engineers create and maintain the interface, I would say mostly the data science creates the interface because he knows best how to graft it on his code. So I think it's more on the ML scientist that activity. Yeah. Sorry for missing these questions at the right slide. I'm jumping a bit back and forth between tabs here. Now, going back to the presentation. So I said for the batch pipelines, we leverage the message queuing for basically for consumption and of the inference. For the online models, this is a bit more complicated because we have situations, and these are complicated for the models which have hundreds of models inside the business case, is that you cannot expose hundreds of endpoints to your consumers. They're hard to manage, to keep track of, and it's just not a good idea. So what we put in front, we put gateways. So we created for the different, for the ones which have more than one model, we have gateways which basically provide this exactly single endpoint of consumption to the outside. And the gateway has the task of receiving the request and then collecting the inference from all the currently running models and delivering the result in one go back to the consumer. It also, of course, satisfies other technical tasks, such as dealing with authentication, scaling, logging of the requests, and in the future, maybe probably also other activities. For the molecular property predictor, we have a single gateway, which is basically hiding the 100+ models behind it, which is very nice because it allows us to add more models. This is what typically happens, that there are always there are more properties being added every few months, And as we have the gateway in front quite transparently, the consumer never knows of that. He just now notices that new properties are being offered, which is quite good for the long-term evolution. Now I will go a bit next to the next let's say interface that we have. So we now talked about the consumers, the producers and the consumers. The third pattern and the last one for this presentation is about an MLOPS SDK. This is one which we started, and we covered a few ground here, but there's still a lot more to be done. And it comes from observation that there is a lot of things that one has to do when you interact with tooling for machine learning deployment and any other activities. So you have to interact with some sort of an orchestrator where you push the pipelines. And that can be Kubeflow, AWS SageMaker pipelines. There are many orchestrators for pipelines, and they're all quite different. And not all of them are that easy to use, and they have some specifics which you most of the time you have to consider if you have quite custom, let's say, needs. Then you have different infrastructure, be that you're deploying to Kubernetes or deploying to SageMaker or another cloud vendor. There are constraints around there to think about the proper permissions, proper access rights, probably many other things to do. Then you have CI/CDs, which are being leveraged on the ops repositories, and sometimes you do things over and over again, or like building containers, packaging things, checking, doing some validity, deploying things. And there are also activities around data access where you're always pulling data from the same buckets or from different activities. And what we observed is that this complexity is quite high. And we thought to ourselves to also help the ML engineer or data scientist is we thought of and we started creating an SDK which wraps many of these activities and hides them from the MLOps engineer, or that hides them in a way, but kind of pushes them aside so he doesn't have to think of these things and just be productive in his activities. And just to highlight just a few activities here. So the Ops SDK initially in our first version was dealing heavily with the orchestrator, right? So it contains different methods, which allows us. It's a bit too small, the text here now that I notice it, but it allows different methods for example, pipeline management. It says here in this first box. So basically, compiling new pipelines, uploading them. This is specifically to Kubeflow, or deleting existing pipelines, listing the ones that are there, and so on and so forth. Other activities are about the run management, so for starting new pipelines, deleting running ones. Then there are also other activities about recurrent runs, which are very important for getting training data and other activities. So overall, this SDK is a third pattern that we applied. It's a Python library, but it's in a way it's a possibility for the ML's engineer in his operationalization repository to start leveraging this SDK for activities which are very common, and you do them all over and over again. And you do not want to. Also, you can make mistakes in these operations, and they have some quirks in them depending on the tool that works in the background. And we try to kind of move that potential of mistakes and to speed up the leveraging of the underlying infrastructure by helping with this SDK in front of the MLOps engineer, but also for the data scientist if he wishes to. Now, with that in mind, I'd like to summarize this a bit, and then I'll probably go to the questions because I'm probably missing a few. We focus on three patterns here, right? So one was the first one that was really helpful for us was a clear separation of the ML, model-related code, and the ops-related code to deal with the diversity in frameworks, languages, dependencies that models have. The second one is the consumption, right? So the two ways of consuming also online inference over gateways and batching, for instance, of message queues is very good at separating and hiding or reducing coupling between producers and consumers. And the last pattern is that common deployment of infrastructure operations, it's great if they're packed in SDK, because this does not put the load on the MLOps engineer to deal with every small consideration in the background, especially when infrastructure sometimes changes, and you do not want to put that load on the on the MLOps engineer. Sorry for that. Now I'd like to go back to the questions because now I can see them on the other page. So, so question for Ishai. So, how can the MLOps engineer leverage distributed computing? Yes, that's a very good question, right? So, I think this is I think the idea with packaging the training in a single container depends. So of course you can have like embarrassingly parallel operations where you could split the training data set and you could leverage the same container. But I think for more complicated activities where you need actually parallelization built inside the training operation, I think that this is where the ML engineer and the data scientists have to work a bit more closely to make that work. But I think that's definitely it's there. You have to invest a bit more effort into making sure that the distributed training also works. No problem. Yes, we're also using GPUs. The monoclonality predictor, the image-based one, it was heavily using GPUs. Yeah, and that was one possibility where data scientists can kind of specify what kind of machine he needs, and that's being then reflected. Okay, let me see if I can get tracked to that. So what the interface looks like. So a question from Benjamin. For pre-processing that is distributed, what part of this goes into the model repo and what goes into the ops repo? That depends a lot. So I don't in our models that we had, I don't recall now how much of them were doing distributed pre-processing. I hope in distributed computing of the pre-processing part. Or maybe I probably totally understand the connection wrong. But the interface in that particular way, it's nothing super complicated. It's basically, it's a container interface. So you have a CLI tool, a click-based tool that is being implemented, that is being provided by the MLOps team. Data scientist basically kind of fills in his interface with these operations that he has, the training, the pre-processing, and whatever he needs to do, and basically builds the container where the entry point for the container is the CLI basically. So you just execute the commands of the container directly on the command line inside the pipelines. Yeah, so that's basically nothing quite sophisticated there, but works very well. Okay, let me go back to the questions. I don't know how much time we still have. Yes, that's a very good question. So from Majd is how do you to upgrade? We don't force them to upgrade. We just make sure we kind of communicate that the newer versions have more features and they're more powerful. And we always try to extend the SDK. So so far we've got the chance to extend it and not to really deprecate certain things. We don't have that much history to start deprecating, but we kind of try to insist on the fact that there are more features in the newer ones and not try to force anybody, because we're maintaining the version of that particular library. Maybe the last question now from Benjamin here for the pattern one. Yes, it's a very good question. It's a very good question. So as I said in the beginning, is that there might not necessarily always be two persons. So it could be a data scientist is also doing the ops part, right? However, for us and in the infrastructure that we have set it in the background, it's much more useful to have this interface because it creates this clear separation of concerns. And we do have situations where data scientists just cannot handle the MLOps part because they're involved in so many other projects where they're contributing. They're relying on a team which is offshore of MLOps engineers, which is basically taking care of the MLOps part. Yeah, so and there is communication, but we're trying to make this interface so simple, and we do have different ways of mitigating this, of exchanging this, so that it actually so far it has worked for us. So I would say that in a way we're trying to kind of mitigate that, but I do agree it can lead to a problem if it goes very, very, very large. Good. Thank you very much for the questions. Very interesting questions. I think that the event is ended. And with that, I thank you so much for your attention. And I'm still online here and in the chat if there are more questions. Thank you also. Have a great rest of the day.